that is the average DC voltage. Average DC voltage or average DC side voltage. So, we use a notation for this, V uppercase V with a subscript D. Now, can I use the table and try to get the average value of the DC side voltage? If there is one cycle and in one cycle there are 6 intervals, the waveform of the DC side voltage actually repeats 6 times. Is that result well known to you? Okay. So, I use that information. So, I know that there is there are actually 6 intervals in one cycle and the waveform repeats. So, the frequency of the DC side voltage is 6 times the frequency of the AC side voltage. So, if I want the average, I need not do an integration over 2 pi radians, I can just do it over 2 pi by 6 radians. Okay. So, what I can do is, I will try to take any one interval is of duration 60 degrees, that is 2 pi by 6. So, I will just integrate over one interval of duration 60 degrees and get the average value. So, 2 pi by 6 or pi by 3. So, 1 by pi by 3. So, I can take any of the 6 intervals. So, the first interval is from alpha to alpha plus 60 degrees. So, if I take the first interval from the table, I have to just substitute for the instantaneous Vd. Okay. So, it is integral of alpha to alpha plus 60 degree of Vd with respect to omega Ot divided by pi by 3. So, that is the expression for average DC voltage. So, that is equal to 3 by pi integral from alpha to alpha plus 60 degrees. Vd from alpha to alpha plus 60 degrees, we know the expression for Vd, the instantaneous Vd from alpha to alpha plus 60 degree. I mean, we got Eb minus Ec. Integrate with respect to omega Ot. Omega Ot is the angle. So, our independent variable is angle. So, we are not using time as the independent variable. Omega O is the operating value of angular frequency. See that subscript O is for operating value and omega is the usual angular frequency. So, omega O is the operating angular frequency. So, this is equal to 3 by pi integral alpha to alpha plus 60 degrees, and of course, Eb minus Ec is root 2 V. So, from the expressions for Eb and Ec, I can get the expression for Eb minus Ec. It is sin omega Ot plus phase angle, which is, so Eb is having a phase angle of 30, Ec is having a phase angle of minus 90. So, minus Ec will have a phase angle of plus. Now, can I straight away say can I straight away write the expression for Eb minus Ec? So, what is it? Plus 60 degrees. Yes. Okay. So, I mean, this is straightforward integration. So, if you integrate this, you get, I mean, I will leave it to you to derive this 3 root 2 by pi V cos alpha. Now, if you recall, we had one more quantity VDO. Do you recall this? This notation VDO, there is another subscript O. What is this VDO? Sorry? Yeah, maximum. Say we use this notation in the context of trying to obtain a general converter circuit. Okay. So, if you use this notation for maximum average DC voltage. So, what is the maximum average DC voltage in this case? Look at the expression for Vd. Vd is the average DC voltage. What is the maximum possible value? So, maximum is obtained by choosing an appropriate value of alpha. So, for a particular value of alpha, if alpha is 0, we get the maximum value. So, that is 3 root 2 by pi into V is the maximum average DC voltage. So, that is VDO. So, therefore, I can relate VD and VDO. VD is VDO cos alpha. Okay. So, this is something which is applicable for the circuit we considered, irrespective of the operation of the converter as a rectifier or an inverter. See, these are not dependent on how the converter operates, whether it operates as a rectifier or an inverter. Now, we have to see when we get rectifier operation and when we do not get rectifier operation, or when we get inverter operation. So, when do we get rectifier operation? Alpha is less than 90. So, you see on the DC side, see, if you look at the DC side of the converter, our assumption is a constant current. So, the DC side has a plus terminal and a minus terminal. The voltage across the DC side is VD. Say I am not drawing the entire circuit diagram. The DC side of the converter has 2 terminals. Okay, the voltage across the terminals is VD, and I have a current ID. Of course, ID is positive. Please note ID is positive. It is a current source. ID is positive. So, that means the converter acts as a rectifier if the average power is flowing from the AC to DC side. That is the definition of rectifier. Okay. So, a converter has distinguishable AC sides and DC side. AC side has 3 terminals. We always work with 3 phase, of course, as far as this course is concerned, and DC side has 2 terminals. So, if the average power flow is from AC to DC side, then we say the converter is acting as a rectifier. If the average power flow is from DC to AC side, it is said to operate as an inverter. So, that is the definition. So, if I look at the average power, what is average power? It is nothing but the average voltage into the current. That is the average power. Current is anyhow constant. Current is a constant value. Please note this ID is constant. That is our assumption. Okay. So, if average power has to be positive, then what should be the value of alpha? So, if alpha is greater than or equal to 0, if alpha is greater than or equal to 0 and less than 90 degrees, then VD is positive. Yeah, there are 2 VDs, one should be careful. I hope I am able to differentiate between the instantaneous VD by using a lowercase v and an uppercase v for the average value. So, the average value of VD should be greater than 0, only then the average power is okay. So, if alpha is between or in fact even equal to 0, greater than or equal to 0 and less than 90, then VD is positive and average power is positive. Average power is positive. So, then the converter operates as a rectifier, then converter operates as a rectifier. Now, if it is equal to 90, if alpha is 90, it is neither a rectifier nor an inverter, there is no power flow. Okay, both, I mean when VD is 0, power is 0. Okay. Suppose alpha is greater than 90, then we get a negative value of VD. If alpha is greater than 90, we get a negative value of the average value of the DC side voltage, then the power is actually flowing in the other direction. Then the converter is said to operate as an inverter. Now, I will come to that later, because I know that if alpha is greater than 90, it is inverter operation, but I still don't know for the time being up to what value of alpha I can go. So, I will come to that a bit later. So, inverter operation will be considered just shortly, but later. So, these are a few things which we are able to obtain from the table that we obtained in the last class. Okay. Now, there is something on the AC side. Say ideally on the AC side we should have voltages and currents that are sinusoidal. On the DC side voltage and current should be constant. Now, if you look at the AC side of the converter, the voltages are sinusoidal. On the DC side current is constant, but the voltage on the DC side is not constant. I mean, it is not a constant. Okay. Similarly, what about the current on the AC side? The currents are not sinusoidal. So, on the AC side voltages are as required ideal, but currents are not sinusoidal. On the DC side current is ideal by our assumption, it is constant, but voltage is not ideal. So, when we say something is not equal to what is desired, then we want to find out by how much it is deviating from ideal. So, how do we do that? We want to quantify the amount by which the voltage on the DC side is deviating from ideal, from the ideal waveform, and we want to quantify the amount by which the current on the AC side is deviating from what is desired. So, how do we do that? Sorry? Sorry? Huh? Ripple factor. Yeah. Any other suggestion? Yeah. So, finally, it is some frequency which is appearing and which should not be there. Say on the DC side we want only DC quantity, but there are other periodic waveforms. So, the point is there are other periodic waveforms that are appearing on the DC side in the case of voltage. On the AC side as well we want only fundamental, but we do not have DC on the AC side, but we have some other harmonic components. So, a very nice way of trying to quantify this is using what is known as harmonic components, and that we can do by the use of Fourier series. Okay. So, what I will do is I will try to briefly give the results of Fourier series without getting into any derivations. So, that you are familiar with the results and one can use directly. Okay.